Let's talk about stereochemistry and isomerism. In this lecture, first I'm going to start by talking about constitutional and stereoisomers, different types of isomers. Then we'll talk about stereoisomerism in more depth. So what is a stereoisomer and the things that make something chiral, the definition of what a stereocenter is, and the definition of what an enantiomer is. As you'll see, isomerism involves lots of definitions, so we'll have to learn these definitions and understand the implications as we analyze different types of isomers. So what are isomers? We've talked about these already before. When we talked about alkanes, we said that the atoms could be bonded in lots of different orders. Those are called isomers. Technically, an isomer is going to be defined as two different compounds. They must be different, but they have the same molecular formula. For example, in some sunscreens, you have para-amino benzoic acid, which has a formula C7H7NO2. If you rearrange those atoms, you can get nitrotoluene. It has the same molecular formula, but it's an explosive. So you can see that it's important to understand the difference between different isomers. Even though they have the same formula, they can have vastly different properties. These are a special kind of isomer called constitutional isomers. Those are isomers where the atoms are connected in a different order. For this chapter, we're going to focus primarily on a different kind of isomer, which are called stereoisomers. So we can subdivide isomers into two broad categories. Constitutional isomers, which we just talked about. Constitutional isomers, we're going to say it's the same formula, but different order of atoms. Whereas stereoisomers, they're going to have the same order. So what's different about them is their arrangement of the atoms. They're different in three-dimensional space. So what do we mean by that? That seems kind of like a weird thing. So let's look at some examples. Some examples that we're already familiar with are cis-trans isomers. So remember, this is cis-1,2-dimethyl cyclohexane, whereas this is trans-1,2-dimethyl cyclohexane. Notice that the atoms in both cases are bonded in the same order. So here you have a carbon that's bonded to a methyl and a hydrogen and two carbons. CH2, 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 carbon bonded to a methyl and a hydrogen. The same order of connectivity. The atoms are bonded in the same order, but notice that we differ in the way that those atoms are arranged in three-dimensional space. In one case, the two methyls are together. In the other case, they're opposite of one another. So these are called stereoisomers, meaning that the atoms are bonded in the same order, but they differ in the way that they're arranged in three-dimensional space. Another example of stereoisomers are these cis-trans isomers. Notice the methyls are together here, they're opposite here, but we still have carbon, 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 carbon. The hydrogens are bonded in the same order, so we have the same order of connectivity, different arrangement in three-dimensional space. Remember, unlike ethane, once we have a double bond, we have this pi bond that restricts rotation. So whereas ethane could freely rotate, this bond cannot rotate, so we get two different isomers. What I wanted to emphasize here actually is that we get different physical properties. These two isomers, even though the atoms are bonded in the same order, the fact that the methyls are arranged differently in three-dimensional space leads to a difference of 3 degrees in the boiling point, and this is going to become important later on in the chapter. Okay, so there's two types of stereoisomers that we want to concern ourselves with. We have enantiomers, which are mirror images of one another, and diastereomers, which are not mirror images. First, we're going to talk about enantiomers. These are going to be stereoisomers that are non-superimposable mirror images. So let's talk about what that means. Imagine this pair of sunglasses, right? If we look at its mirror image, right, these two things are mirror images of one another, but notice, if we took the mirror image of this pair of sunglasses and flipped it around, they would be the same. So since these two things are the same, that's the same as saying superimposable, meaning that we could superimpose the mirror image of this on itself, meaning that they're the same. But notice the difference here, right? If we took this pair of sunglasses with one lens missing, its mirror image is not superimposable, because if we took that pair and flipped it around, now this purple lens would be over here, meaning that we had two different pairs of sunglasses are that they're not superimposable. Let me show you. Right? So these two would be the same, but these two are different. They're not superimposable. We can't superimpose its mirror image on itself. So what we said is that enantiomers are going to be non-superimposable mirror images, and another word for this, something whose mirror image is not superimposable, we're going to call that chiral, meaning that its mirror image is not superimposable. Okay, another thing about chiral compounds, or chiral objects, is that they lack an internal mirror plane. The word chiral is derived from the Greek word for hand. Notice that your two hands are mirror images of one another, but we can't superimpose them on one another. So the reason is because you have no internal mirror plane in your hand. But if you look at a hammer, for example, if we take the mirror image of a hammer, we can just take that hammer, rotate it around. Those things are the same. Those are superimposable. And that's because there's a mirror plane inside the object that bisects this half and the back half. So since this contains an internal mirror plane, that means this object is not chiral. So hands are chiral, hammers are achiral. Let's look at some more examples. So when I say internal mirror plane, what I mean is that we could bisect this kitty cat's face in half. So this is achiral, meaning that it possesses an internal mirror plane. Similarly, this chair, I did not draw it very well, but this is also achiral because it possesses an internal mirror plane. This basketball has an internal mirror plane like that, so it's also achiral. But notice this climbing shoe does not have an internal mirror plane, so its mirror image would not be superimposable. You'd have a left and a right shoe which would not superimpose on one another. So a climbing shoe is going to be an example of a chiral compound. We're going to look at this with molecules, not really with climbing shoes very much. So take these two molecules as an example. You have a OH, a hydrogen, a methyl, and an ethyl group. If we look at the mirror image of this compound, if you imagine taking the compound on the right side and flipping it over, right, this methyl would flip over to where the ethyl was, and this ethyl would flip over to the methyl. So if we took this compound and flipped it around over here, what would that look like? We'd have OH and hydrogen, but we'd have methyl going back, and we'd have ethyl coming up. So these two are different. They're not superimposed on one another. And one thing that we're going to notice is that in this class, especially, chiral compounds are going to possess a stereocenter, which is a carbon that's bonded to 4 different groups. So this is called a stereocenter, meaning that it's a carbon that's bonded to 4 different groups. That's going to make this compound chiral in this particular case. A stereocenter, we're going to define that as a carbon bonded to 4 different groups. Okay, so let's identify the stereocenters in these molecules. This can be kind of subtle, right? Because notice this is a carbon. In this case, it's bonded to a chlorine and a hydrogen and a carbon, but we're looking at the entire group. So this ethyl group is different than this methyl group, so this is a stereocenter. This is a stereocenter because we have an OH and a hydrogen and an ethyl and a propyl group. Just because these two are carbons doesn't mean that it's not a stereocenter. Those are 2 different groups. Similarly here, we have a hydrogen and a bromine and a carbon with a double bond and a carbon that doesn't have a double bond, so this is a stereocenter. What we're going to say is that all chiral compounds in this class, all we're going to be worried about are chiral compounds that contain stereocenters. But be careful, because just because something contains a stereocenter doesn't necessarily mean that it's chiral. We'll see some examples, but all chiral compounds will contain stereocenters. Okay, so we defined a lot of things. Let's go over them quickly before we're done. We said constitutional isomers are going to be defined as 2 different compounds that have the same formula, but the order in which the atoms are bonded to one another is different. Those differ from stereoisomers, right, because the atoms are bonded in the same order. They just differ in the way that they're arranged in 3-dimensional space. One type of stereoisomers that we talked about were enantiomers. These are stereoisomers that have non-superimposable mirror images. We call those kinds of compounds chiral. So enantiomers are chiral, and chiral compounds possess a non-superimposable mirror images. But remember also, this is going to be important, that all chiral compounds lack an internal mirror plane. Like the climbing shoe, all chiral compounds are not going to have an internal mirror plane. That's going to be important later.